Yes, as the security guards, I thought security guard is inquiring him. Yes, as the security guards actor. He asked me.
Oh, strange. Is he? Yeah, signal. Wi-Fi.
It's not Wi-Fi. Now it's blank screen. Can you stop my screen?
You already disconnected from the phone. Yes. Can you just disconnect the power? In the keynote, right?
Yes.
Like my table in the laptop. I mean, now it's just that. That's a laptop hanger.
Yes, it's backed up on Google Drive. Sure. It's restarting. Let's give it one more try. So as soon as I screen shared, it just became black. And I saw that the keyboard is active, but nothing was happening on the screen.
ये मेल की जा नहीं रहा है तो अच्छा ठीक है नहीं सब इसमें क्या सब ठीक ठीक चल रहा था क्या क्यों उसके
So you found it. One more year you in the group. Why not?
हाँ
Why not?
what does a picture compare that? You have not seen that. You
No,
have
I did not see. Yeah,
Ah.
I also didn't see it.
Yogesh का मिला है ना कि if you use a mail client, then I think the SMTP server is not responding.
Oh, so basically,
No. So
I have stopped using SMTP because there are some mails which never get forwarded. I didn't understand.
सब चलता है use the secure server and authenticator and everything चल रहा था मेरा तो समझ आता है but then there is this
As soon as I started messing things, I said, your mail will not go the mail will not go and go to your कोई तो देख रहा है मेरा कंट्रोल
Just the voltage. With the last time. Suffered from.
Just for what functions. Really have happenings and no, no, sure. See? Like, then we tell the what is it?
When there is a we saw some things which were circulated.
I think some people know. It's like out of this conversation.
But I will see the contrast. Amazing. I went to our class. This was he said, well, yes, we have exploring the case.
I think it's clearing the wrong screen.
Yeah, I did. So not observing oh, carry these to the first restaurant. What you do?
First extra one.
कोई भी नहीं जाएगा.
But I'm going to show the screen.
Yes, no, or it is
Just try to share this. Now,
oh no I can do
No, you have to select the wrong.
I will edit it.
I think the point is very serious, I tried to ask person who I could ask, please to go, where's that point?
Where did it go? It is still
So I'm not sure if the question conversion for how that was now share it with the meeting. So maybe but it what apparently they have 15 minutes.
this one.
Once the thing is done.
No, you can drag.
Next.
So I can see. Now can
So I
can slides and see what
adapter.
Adapter मेरा अपना PC पर.
Okay. I'm going regular to have 19 something, but it is not it's possible that you guys get settled and you don't see number. It's the question for since this is still not open, this construction thing, hard hats staying here catching the radar. Okay, don't break up for me back.
No, it's just a shot and shake. It's chicken that.
It's actually nice. Actually, I'm a brick splitting thing. That's whatever.
So, the laser is also not a
Not to worry about for aspects there and what the doing it is. We just have.
a point.
What would say we have the technical standpoint and stuff. It shows it happens even after we don't do it.
When speaking of done like that, I will ask.
Yeah.
These fellows are in plan technical idea of what is this other.
Which
Whatever there is another.
yeah, so I think you need to, because that's the one that is connected. Yeah. So we are waiting for a couple of more minutes. I think we have to start the live streaming.
So this is on.
Say
Sorry.
Okay, I think we are ready. All right, so welcome to today's colloquium. Today we have Sourav Chatterjee, and he spent a lot of times in various different institutes. So I had to print it. Okay, so starting from BSc from Jadavpur, MSc from IIT Kanpur, MS in Northwest Western University in Illinois. Also did PhD from the same university in 2010, and then he did I think a couple of postdocs, one at University of Florida, and then he was how do you call it, CIERA Sierra fellow from 2014 to 2018, and then he was also served as a research assistant professor, and again in Northwestern University. And then he joined at TIFR as assistant professor in 2018. Now he is an associate professor there, and he has a long list of research interests as well. Like he studies astrophysics of gravitational wave observation. I think that's the subject of today's topic. And then exoplanets, stellar dynamics, and compact object binaries. So welcome, Saurabh. And we have 1 hour from. So I'll give you 10 minutes.
Okay, thank you. Thanks for the introduction, and thanks a lot for the invitation. It's a real pleasure to come to IUCAA. I did my BSRT in IUCAA, and I sat in these chairs as a student, wondering about all the fantastic things you guys were teaching me. So it's really nice to stand here and speak to you. And in that vein, I targeted this talk for the students, like sitting over there, mostly, I see. So if you are a gravitational wave expert, then bear with me. See if some of these are somewhat basic for you. So today I will talk about the astrophysical formation of gravitational wave sources. And I will take a somewhat like a forward modeling point of view. So I will start without noticing what we have discovered. We will try to understand the astrophysical processes that can create systems that we end up observing. And we will try to go to the basics and try to get as much pedagogical understanding of this formation as possible. That's the main goal. Okay. I'll just use this.
Click on this.
And now you use the digital version.
Now I can go on. Okay, so you have all seen pictures of this kind, some variation. We have observed many gravitational wave sources, and most of them are two black holes merging. And we believe that these are all of these have stellar origin. They're back formed from some kind of holes. And what we really want to understand is how do you form configurations that will end up merging to be detected through color. So in today's talk, I will talk a little bit about the different astrophysical formation channels that we know of. And then I will dig slightly deeper into the processes that are responsible for the dynamical assembly channel. And then I will specifically talk about the formation of mass gap and intermediate holes. So these are holes that are very massive, and we do not expect normal stellar evolution for but we have observed that. So we will talk about the channels and exactly kinds of things that actually determine what channel becomes what at what times. And then I will talk a little bit about the uncertainties in and challenges in completely understanding the situation and rates and distribution, etc., and some potential way forward. This is extremely biased from what I am interested in, and so on. So, if you want to create two black holes, or actually any compact by the way, I will in general keep saying black holes, but pretty much everything that I say black hole can be transferred to neutron stars. So if you just zoom out and say, okay, I want two black holes that will merge, and that's what I want to detect, then you first start with two massive stars that's in a binary. So this is the isolated evolution of scalar binaries. That's the most straightforward picture that you can think of. You start with two massive stars in binary. Then both of these stars become two black holes, still in a binary. And these black holes emit some gravitational waves and become a bigger black than each. And that's what you did. Okay. It's a very straightforward picture, but straightforward does not necessarily mean it's simple. Okay. And this is the reason. Okay, so this is like Astro 101. So if you start with a massive star, and it has some core, that's where all the nuclear fusion and all the magic is happening. There is some envelope that's not doing too much in terms of energetics. But over time, before it can become a compact object, it becomes a very extended object. Okay. So the core shrinks, the envelope becomes really large. In the end, depending on what is the core mass, you create white dwarfs, neutron stars, or black holes. And all of these numbers, take it with a grain of salt. We do not exactly know what is the exact boundary numbers. That depends very strongly on many different uncertainties. Another thing that you need to pay attention to is that these massive stars, before they become compact objects, can become really large. So this is about 100 solar radius to about 1,000 solar radius. Okay, so why does that matter? I'll come to it in a bit. In addition to becoming very large, at the time of compact object formation, the star loses dramatic amount of mass. So if you look at the best models that we have so far, so this is the initial COH length sequence mass of a star. So you can see that it goes from 20 to 140. And then the final mass, that depends on the metallicity of the star, that's about 40, right? And less. So imagine that you start with a 100 solar mass star, and that ends up producing a 40 solar mass compact object. That is 100 solar mass worth of material just ejected from the system. So that's a lot of lost mass. So what's the significance of this? So for the first picture, the simple picture that I mentioned, for that to work, you need this condition. The binary must not break. Okay. So the significant mass loss, what does it do? It makes the overall binding energy very low, so the whole orbit expands enormous. On top of that, when this mass is lost during contact of formation, there is no reason to expect that it's exactly spherically symmetric. So any small asymmetry will end up giving a kick, this Newton's theorem. Okay. So these metal kicks in very wide binaries can easily break these binaries. Right? So in the end, what you need is that this binary must not merge before becoming the compact. Otherwise, you will have two giant stars splitting, not two black holes. And then the final compact object binary must be compact enough to merge within a Hubble. And together, these two conditions are attacking you from two different ends. Right? So if you look at the Peters equation, so this is the orbit average equation that basically tells you how the same axis shrinks through gravitational wave radiation. That is a very strong function of the separation between the two masses. Okay. Now you remember from my initial cartoon that stars become as large as few hundred to few thousand solar rays. So let's put this time scale in perspective. So if you cannot read these numbers, so this is basically the separation in terms of the solar radius, and this is 10 to the minus 3, and this is 10 to the 3. And this is the in-spiral time scale in gigayear. So that's basically Hubble time. So anything that emerges before Hubble time, that's the only ones that merge in our universe, and to be technical, must happen in this pink region. Okay. And this is the limiting separation that you need. Anything that's more separated than that will not merge and not relevant for gravitational resources. But you see,
Assuming that there is nothing else, which means
it's
just by gravitational.
this is just by gravitation. But you need the initial stars to be more separated than this line because the stars become that. Okay. So this is not really a problem anymore. We understand why, how this shrinking happens. This is what is called the common envelope illusion. When stars become very big, it becomes very hard for them to retain its mass. So there is mass transfer. If mass transfer is too fast, then the heater cannot accept all the mass, and the mass engulfs both objects. That is the common envelope is created. In this common envelope, this becomes a highly dissipative thing, and these two cores are basically orbiting each other in a very dense gas, and that can quickly shrink. And that's what you need. Yes.
Now, then you have computational evidences for this one, the being like
Yes, there are many contact binaries. So any contact binary is kind of like a common envelope. If it is exactly a common envelope, it becomes very hard to know what is inside that. But there is enough evidence to understand. Okay, so using common envelope evolution, you can shrink these orbits to where you need so that they can. Now, when we understand this is a very hard problem to solve from first principles. Okay, so the time scales are enormous. Usually the way we solve this or do forward modeling is through based in prescriptions. Okay, so the two things that really matter is what is the coupling between the orbital binding energy and the heat that goes into ejecting the envelope in the end. and what is the viscosity that basically tells you how quickly you think. So by playing with these two numbers, it turns out you can get pretty much anything that creates issues.
So that's like, this is like after the first supernova, right? If there is a supernova within the common envelope, then that the binary will break.
Yes. So it can be, you have two chances.
In the 100 times, 1,000 times you are saying in that red giant space.
Right.
So it becomes bigger, but after that, when there's collapse, then there will be like a shock wave going, right? And that, like at some point, there will be a
So there are, so I think I understand what you were asking. So there are two chances of common envelope. So one star evolves faster, that's the actor that flies the envelope. Then the other scope is the next star evolves, and that can also create an envelope. And in simulations, we see all kinds of combinations. Some binaries come from two common envelopes, some creates a common envelope for the second star, create the common envelope for the first star. So let me just quickly give you an example. So this is from Benchinsky's paper. It came out immediately after the first detection, and they tried to, in their binary population synthesis, they just tried to find a merger that looked exactly like the first merger. This is where the common envelope magic is. So here I'm showing you the separation. This is the eccentricity, doesn't matter for this talk. And these are the masses and times, etc. So you see that the second object, so this is already a black hole. This is the second object that's creating the common envelope. And then this is the shrinking, okay? It used to be 3,780 solar radii apart. That shrunk to only 43.8. And then these created a black hole, and then two black holes. Okay? But this is a particular example. You can find many different combinations.
the wind pressure is much larger than on a black. It is compact black hole. Because there is a mass law, like that will have a lot of most pressure on the because other star has not it's not compact, it's a normal star. It can just push it away, right?
Mostly you would think of like the effective potential is changed. The matter will flow like that only. It is not like environment you are pushing. It's not like the other guy.
No, I'm saying it's quite different. There is a shock wave, right? Here,
So supernova,
it's not here.
There is no supernova. I will think like photosphere, without looking at 1 hour R square, 1 hour R potential. It is getting it's like a Roche flow. Right? It's an extreme condition of Roche flow.
yeah. So whenever you have supernova can do very destructive things. So depending on the key, it can even make the binary, and you may find the compact objects sitting somewhere else, leaving everything. So, and all of these, you have to realize that these are all prescription-based calculations. Nothing better can be done.
Time scale of this kind of, for example, the one you have bracketed. I would guess that even a spectrum will be very different because you have disturbed the photosphere.
Uh-huh.
Whereas you would not have, I don't know, so is it possible to detect this thing in large spectroscopic surveys? Whether is there anything is there?
See, the time scale is very short. The time scale is very short. So between 3.8 million years, when it started the common envelope evolution at 5.0445 million years.
It's good.
Yeah. So it happens almost immediately. But that is
Coupled with the fact that you are detecting so many binaries, you have to do something, right? If you go this way, there should be no binary. You will say, no, this okay, this is not the method.
So this alpha and lambda. So alpha is the effective viscosity, and lambda is you can see over length between the orbital binding energy and the envelope. So these are tuned to match the relative numbers of CDs and other electronical objects. But how accurate that is up for debate, and people do play with this is the range of uncertainty I will allow, and that gives you error bars and different types of things. But that's kind of the state of the art. So there is another channel. So this is called the chemically homogeneous evolution in closed binaries. So here, so remember in the previous one, the main challenge is that the stars become, and then you need to bring them. Here, the stars do not become big. So the only reason stars become big is because there is a clear separation between the core and the envelope. And that happens because there is an entropy barrier. So whenever you create heavier nuclear, you stay refined in the, and the envelope does not get into the to nuclear fusion. But if you can have very massive stars that are very close to each other and tidally low, then the spin becomes equal to the orbital period. And then through centrifugal force, you can break the entropy barrier and you can supply hydrogen from throughout the star to the, and you essentially never go to a giant phase. You always remain in a very peculiar main sequence phase, and the star never expands. In the end, the whole thing becomes a helium star, and then the whole thing becomes a black hole, never expanding. So that's the idea. So far, I don't think there are a lot of evidence that this actually happens, but there is also no evidence that this can happen. Okay. But if this can happen, then you can explain some of the sources, but this works only in a very limited space. So this is taken from Mendel and Levine, and this is the companion. So this is equal mass binaries, and you can see that if the orbital period is here, it becomes normal evolution because tidal locking didn't happen. If this is here, then Roche-Low overflow starts at 0h, so it doesn't work. Only in this parameter space you can have any hope to do homogeneous. So even if this works, this cannot explain all kinds of sources.
Actually calculate the yields are different for these stars compared to normal level.
Yes, the mass ratios, the mass ratio difficulty.
Chemically, because you are maintaining the equilibrium nucleosynthesis over a larger period, right?
Right.
Compared to any disturbances. Will it produce different elemental ratio?
So the standard picture of chemically homogeneous solution is nothing is lost. So the whole thing becomes
Anyway, but what I mean is that during this, see, again, I'm thinking which way you can detect. For example, whether number of neutrinos coming out of these stars will be different from number of neutrinos coming from things like this. Is there a probe where one can use?
I don't know. I'll have to check.
So otherwise, they all look like stories, right? You have to predict something which.
Right. Yeah.
Okay.
What I have read so far, they are kind of stories. I haven't seen any like the yield papers.
These are isotopes. All these things will be interesting, right?
Right.
All surveys going on. So
That's why even if you say 1 out of a million, you will be able to detect it.
At least we will get some relative thing. Even that will be significant numbers. There is, of course, this very interesting idea that maybe all these black holes are living in Aegean disks. And then, so this is very interesting for theorists. So this is extremely rich in physics. You can pretty much do anything because there is no observational evidence yet. So that's like a theorist's playground. You can do quasi-Lydov oscillations with the supermassive black hole. The interactions are confined to the disk. And then you can have resonant orbits, migration traps, all kinds of physics that are interesting for planetary physics, you can apply them now for black holes. Okay, so this is very interesting, but I will not cover this in future. So other completely different channel is the dynamical cluster. So this happens in dense clusters. So this is just a picture of a globular cluster, and this is just a movie. This is a movie. So this was actually created for Adler Planetarium in Chicago. So they were. So what you see is that the stars are interacting quite rapidly. So these are extremely dynamically violent, and stars collide with other stars. Strong encounters happen all the time, and you can create all kinds of very strange looking objects.
What are these
So these were the common. So white dwarfs were, I think, dwarfs are red, neutrons are something like something. So we could not figure out how to show the compact objects, so we decided to make them. So although I'm kind of telling you stories, whenever actual simulation results, the simulation results will be from the CNC cosmic simulations. So this is a very good code. It contains all relevant physics. In the end, you get results that can be directly compared with observations of globular clusters. For example, this is actually a visual band rendering of one of our simulations. This is not actually really. It looks exactly like. In the end, you get all stars with all their evolution and kinematic history. In the end, you can create beautiful surface practice profiles and those illustration profiles.
The simulations, they're like point particles simulated as stars with isolated evolution, or like if some things get too close, or maybe there are binaries or something. Is that
so? All single star evolution, binary interaction physics, tidal capture, collisions, yeah, all of that is tracked.
So he's saying that photosphere is included in the idea. Will you allow evolution of
Yes,
photosphere, or is the point?
stars have masses and radii, effective temperatures, volumetric luminosities.
They're allowed to go through some scaling relations.
it's a large dynamical range that you need to simulate?
Yes. And the way we overcome this challenge is different things are happening at different aspects. So they can be separated out. So for example, if we know that there is a binary, say 1AU binary, I do not need to track its like it's two separate n-body particles. I can call it the center of mass as the n-body particle that's taking part in the two relaxation process. But then, unless something can change the orbit, I keep the orbit same.
This will happen, right?
This will happen. And then, so separately, we treat strong encounters. Binaries take part in strong encounters. These we track with full n-body. Then this binary can interact between themselves, mass transfer. We treat with stellar evolution routines and so on.
What is your mass resolution?
Every star.
That's,
This is a star by star.
then initial condition is what? So you don't realize this to get see the density profile. What you are saying is it what is given?
No, this is in the end. This is in the end.
So you start with some random distribution of star.
This is so the most common practice for us is we start in. And then we put in the IMF of choice, and then binary fraction of choice, but then the distributions we decide. So the big thing that we still do is all stars and binaries form at the same. Okay, so if you are very interested in star cluster formation, for example, we are not quite tracking that.
Also to be initiating the binary sound capture. We can 10%.
So for star clusters, dense star clusters, 5 to 10% is what we.
So this is a key profile. How do you set the velocity distribution?
So the king profile is determined by the center of mass.
So you don't consider binary there because it is a distribution from the single part,
Yes. Yes.
not the binary part.
That's what he's saying. For some calculation, you take the center of mass.
But then
In setting up,
the center of.
So are you talking about how to define the phase space?
Yes, yes.
Okay.
That's what the doctor.
So
It's not a.
so you create the phase space using king. Then you put in an ion. Okay.
Related to the velocity.
So and then you
well, that's the question, but it will not be affected.
Two particles different thing than the single part.
no, but the binaries
It's a
are
small
not.
number, that's the real number, it's a few percent.
So, and binaries are for all for the purpose of the king file and the relaxation. This is not a binary at all. It's the total mass of the binary sitting at the center of it. And you can tell what is for the center. No, the individual particles will have its binary.
But when you have a binary, which is a fraction, which is changing,
Yes, and then you
then your distribution function is all.
that is changing.
And then you are not either in the collision lens regime or in the program. Which one?
No, this is always collision. So you cannot start collisional and introduce a few binaries and suddenly it becomes common. So this remains collision. And initially we set up with a king profile. And the profile does not stay the same. It's changing. I probably should have kept some. Actually, I have. I will show you how much things change. So let's talk about the relevant physical processes here. So if you have two stars, so this is there can be separation of the regular motion force grain. Then sometimes they will have a deflection, and in this deflection, if one star loses energy, it sinks deeper into the potential. It now speeds up, so now it has more energy to lose. This continues, and this is a process. On top of that, if you have different masses, then higher mass things will have mass segregation to sink straight to the center. So two-body relaxation and dynamical friction leads to mass segregation. Okay, and then the effect of that is if you have a mix of say black holes and normal stars, black holes becoming more massive will sink. So let's look at some of the relevant time scales. So the relaxation time scale is related to the crossing time through the number of objects. And then for globular clusters, the crossing time is about 10 to the 5 years, relaxation time is about 10 to the 9 years, and age is about 10 to the 10 years. So all of these systems are relaxed. And then the segregation time scale is about the mass ratio times the relaxation time scale. So if you are considering a 10 solar mass black hole, let's say, and the average stellar mass is 0.5, so this is 1/20th the relaxation time scale. So you expect that the black holes have 1/200th of the relaxation time. So it has 200 times the time it requires segregation.
My question was that see, the almost as much more messy than the black holes in general. Or in other words, like when you get a black hole, stuff.
No, what matters is if you look at the Krupa MF, Salpeter MF, take any ion, the overall contribution in mass is dominated by the low mass.
Okay, so that is
So this is a very, very peculiar regime. So the total mass is dominated by the tiny guys. The energetics is completely dominated by the massive guys. So only a few are dictating what to do to the cluster. I shouldn't be too surprising in today's.
require the heavier objects Why not the normal star? The heavy stars also come to the.
It does. It does.
Okay.
But that's like 3 million years.
They were on the way, they become black holes. So, on the way, they become complete part times.
In the air, I see what was. Yeah.
So I called it black holes, but imagining them as black things are massive. And this tension between mass segregation timescale and evolution timescale of high mass stars will become the story of something later. So, yeah. All right. So, and this is a direct simulation result as a function of time. And this I'm showing you the core radius in black and the half mass radius in blue. And every time you see a spike, that's one episode of mass segregation. And then these black holes do violent things and eject some black holes or just extract energy from some black hole binaries. And then the whole cluster expands. And then it mass segregates again, expands. And these go on. Right?
What is scale as well?
Yes. We also have tidal compression.
What is the scale?
Sorry?
Fusion in the whole.
Often they are escape times. Often they are escape.
The number of black holes maximum will be fixed in 100 million years. That's not right. Well, are you
And
forming?
then it will slowly eject.
The number will come down or stay there because you're
Come
not
down.
going to have any massive stars form later. It's like a single star burst distributed in a particular form and you're able.
Yes. Yes. So the maximum number of black holes you can produce is predetermined. Because,
I am open mass of the mixture.
and then what these black holes will exactly do, that is chaotic. And then once you have collected all these black holes, then you can have these strong encounters. Here I am showing you actually a binary single encounter. Two red things were in a binary, they came and interacted with the blue thing. Now imagine that the blue thing is a black hole. It has a higher chance of ejecting one of the red things because it's lower mass. And in the end, you will see that a blue thing and a red thing combine and creates a black hole normal star. See? And if you repeat this one more time, it will become a blue thing by. Okay. So it becomes very easy to produce black hole binaries. And this is how you see, let's say the most massive black holes sink to the center. First is black holes or black hole progenitors do not need to be in a binary initially. Okay, so this is very different from isolated evolution. Okay, so you needed to somehow keep the binary intact, right? Here, you do not, it doesn't matter. Form a black hole somewhere, you form another black hole somewhere, they just naturally come and combine. And then you can create binary black holes through exchange encounters, three-body binary diffraction, gravitational wave capture. Okay, these are the three methods. And then what happens after you form a black hole? So typically, once you form a black hole binary, its binding energy is pretty high, so it becomes very hard to break this binary. So through repeated strong encounters, the orbit keeps shrinking. And how much can you shrink? That is determined by how much recoil typical strong give. And if the recoil speed is above the escape speed, then you eject this black hole binary and it will seek alone and mark itself. So in the end, if you think about it, the properties of these binary black holes do not depend at all on the birth rate. It is completely determined by the cluster dynamic. Okay. So here is an extreme example of what is the implication of this. So I will show you results from two identical clusters, but in one, let's call it the red cluster, the initial high mass binary search was 100%. In the black cluster, it's 0%. So in the black cluster, in isolated evolution, you form 0 black hole. If you look at in the cluster, roughly after a few billion years, so that's several relaxation times, you form exactly the same number. So let me just skip a few of this. I thought that I will talk about some average effect. So you basically can just look at typical mass segregation timescales, in spiral timescale, interaction timescale, like very broad brush assumptions. You see, like the time scales of relevance are dependent on mass in this following way. So this is the mass segregation time scale. This is the interaction time scale, and that is how much hardening you can do before the black hole binary is ejected from the scale. Okay, and this is the overall, time scale thing. Okay, and so the way to read this. So don't worry about these numbers too much. So this is the part where clusters become very efficient in forming black hole as quickly as possible. Okay? So roughly 10 to the 5 to 10 to the 7. So clusters are very efficient in forming certain. And if you look at the globular cluster mass function, it also peaks around there. So not only star clusters per star very efficient in creating marginal, nature somehow decided to create clusters with those properties most often. Okay, so this is some conspiracy of whoever you believe in. Now, so we overall understand the broad picture. Now let's go to something that's really interesting. So this is now about black holes that are too massive to be formed through stellar evolution. Okay, and there are reasons to believe that there is a cap. Okay, so let's not go into the details, but roughly speaking, so this is, for example, zero for the zero metallicity. You see that you create compact objects, but then there is this region where you do not create compact objects, and this is roughly the range where you do not expect black holes. So this is the mass gap. Okay. But lo and behold, we see black holes that are in this mass gap. So how do you create them? And some bragging rights. So this is Ilya Mendel, Daniel Holz, and Chris Belczynski, rest his soul, Rodriguez, and me. We took a bet that within the first 100 detections, we will see one margin where the free margin mass will be in the mass gap order. Right? And that was done in 2017, where there were not many detections. And within the first 50, I think, we found 1905. So that made me happy. Because of COVID, I still didn't get my wine bottle.
Now that he's showing.
Anyway, so what are the processes? So this is what we predicted will happen. So if you have two black holes that merge, and so you get to keep this black hole, then this black hole will behave like any other hole and can acquire another black hole and merge again. And this black hole has no responsibility to satisfy. So this is what we call repeated. So since then, there is this another channel that was proposed. So if you start with two massive stars that has different envelope to core ratios, and both of these massive stars are evolving like normal stars. But then in a dense cluster, they may merge. But now they have a very peculiar core to envelope ratio. Okay. And then you can, in some parameter space, this core is not above this pulsational instability threshold. So it does not blow things up. But the envelope has a lot of this. So this becomes a normal black hole first, and then a lot of this envelope then falls back onto the black hole, and eventually this black hole grows into the mass gap. Okay. So we wanted to check which of these matters. Okay. So we did a lot of simulations. So this was with Gonzalez. So we just changed the high mass binary function, and we just said 100%, 0%. And we found that for the 0%, there is hardly any high mass black holes that you form. And for 100%, you form several through this collisional jet. And that was really strange because you remember I said that nothing matters, but it turned out. And then we were very confused. And then we realized that the way we are assigning the binaries, we ended up creating, giving way more number of massive stars overall for the 100% case. So you wanted to get rid of this confusion. So Ambrish, Khurana, my ex-PhD students ran some new models. So these are just initial conditions, not very interesting. But he set things up in a way that the total number of massive stars is exactly. Okay? And which what fraction of these massive stars are binaries, we are just controlling them. And we still see being in binaries makes a difference in collisions. And we actually see that if you look at the binary fraction and number of high mass black holes per model, and this is the maximum mass in black hole created in the model, all of these correlates. Okay. And we were trying to figure out why. And then we looked at the collision map as a function of time. So this is the central density, and it's where the collision happens and when the. Okay. And you see that the high mass collisions are extremely concentrated within the 3 to 6 millimeters. Okay. And the reason is that the mass segregation here competes with rapid expansion due to compact objects. So when compact objects form, because of the mass force, clusters rapidly expand and the density rapidly goes down, significantly decreasing the interaction. And you have only a little window of time. Okay, so density increasing and then suddenly starts decreasing. Okay, and if you put the finer stars in binaries, then the mass segregation is just enhanced by a factor of 1 plus q, q being the mass ratio.
So do you see that then the binary fractions are progressively higher center?
In the central part, yes. Binary fraction within the core always increases. Binary fraction, overall binary fraction remains roughly. So
That will anyway happen due to dynamical friction.
yes,
It's like acting like a.
if you bring binaries faster to the center, you also have binaries. Okay, so we understand why. And then we looked at what's the overall implication of this, and we find that actually repeated mergers happen much more soon. So if you look overall, that does not care at all about the binary fraction. And if you then look at observables, like if you shift, merger time, the differences are over there beyond redshift of 1. This is assuming that all clusters are about 10. So future detectors that can have left times beyond, say, 1 redshift of 1, or if we find that clusters can form much later, like there are a lot of contributions from younger clusters, then we can see effects of these binaries.
What redshift you start your
So we consider that all clusters in this work formed at 10 gigayears. So 0 means 10 gigayears. So whatever that is reflected in redshift. So let me just, so that is just, sorry. These numbers, this is the number of black hole mergers per now. No, as a function of time.
This is a 10 to the 6 solar mass cluster.
This is actually, so initially about 500,000. That's the median. So let me just jump ahead. So this is something that I promised I would share this. Oh. What did I do?
Is it not the same file?
Or he can escape. It's okay.
Wait, sorry.
You need to play to find that.
Very sorry. So this is my list of uncertainties I like. Okay, so as you can see that there are lots of uncertainties. And the ones that are in violet, I think are more uncertain than, okay. So, and long story short, I think what we really want to do is if we want to connect compact object properties to those of their progenitors. So we right now we do not have a, and no matter how many gravitational wave sources you see, since you are only seeing the compact objects, you have no information about the progenitors. And the other thing about the star clusters, although we understand the dynamics very well, and so much so that these can be made in stories, we do not understand very well observationally the star cluster formation over cosmology. Okay? So these are the main sources of uncertainty in any rate calculation that you see provided by anyone, any group. So we have started working on this. We discussed a lot with Amal, but I will focus on some of the efforts along these lines. So basically, what we really want is we want to discover a lot of compact object boundaries where somehow we can put some constraints on the age of the compact object and the metallicity of the progenitor. Okay, and I think Gaia is going to be instrumental for this. So what does Gaia do? So if you have a binary with a compact object and a luminous companion, then there are two things you can measure. So you can measure the astrometric motion of this thing. Okay, so there is parallax, there is proper motion on top of that binary orbit. And then if the conditions are right, then the star itself will be somewhat oblate. So in different phases, its projected size will be different. So it's photometric variation. So Chirag, another ex-student, did very realistic of simulation to find out a population that we expect to be in the midfield. Okay, so it includes reddening, extinction, where we expect a lot of star formation, when we expect that star formation to occur. All of these was taken. And then we asked, okay, so how many such binaries will Gaia get? End of mission. And this is what we find. So this is the white dwarf. Oh, by the way, so there are two different supernova prescriptions used. And depending on that, you get roughly 1 million white dwarf luminous companion binaries, a few thousand neutron star binaries, and a few hundred binaries. So that completely changes the picture because, and this, by the way, is so far consistent with what we have already found. 3. And there is a possibility that you find the same binaries through multiple different methods, and there is a scope for follow-up. The other interesting thing is there is a large range in black hole mass and metallicity range that we expect to find. And the other really interesting aspect is that these are what you can find is dependent very strongly on the luminous component, not the compact object. So the intrinsic and observed population are very similar. That is very different from what, for example, observed population is. And in each of these compact objects, since you are seeing the luminous component, and since you know the distance to the luminous component, you can find the volumetric luminosity and effective temperature. You can use your favorite evolution models to find the properties and then infer the properties of the projector. So I think that is something to be very excited about. And then Onindo is sitting here, and he did some work. So this is about finding compact object binaries. And the idea was basically, so Gaia is not only an astrometric database, it's also a photometric database. So what he did is the following. So he found the galaxy counterparts. And if you look at the FUV, the UV color magnitude diagram, you can clearly see that there is this hot component and the cold component. So these are likely white dwarfs. And then if you plot the same exact stars in optical using Gaia observations, then a lot of these orange points go and sit in the main sequence. And this is expected from population synthesis as well. So we expect that a lot of white dwarf luminous companion binaries are actually embedded in the main sequence. And that no previous survey, because it's really hard to find. So usually people target here or here in surface. So we identify those that jump from here to here to the main sequence. And then we he created a spectral energy distribution for these objects and identified those where a white dwarf combined with a main sequence spectra actually feed the data very well. And then we find 80 new well-characterized white dwarfs within 100%. So that made us very happy because so other surveys have already found a lot of white dwarfs. And within 100%, we still find 80 new. Okay, we find all that they found and 80 new. So that made us pretty happy. And this is just a picture of what the situation is within 100%. So these are all the Gaia stars. And then these red triangles are all the white dwarfs that other surveys found within 100%. So you see that that populates a very different region from the same way. And these yellow circles are the ones that we found. So overall, I'll end here. So the take-home points are that you now know if you didn't before the various astrophysical formation channels and what are special about each of these and what conditions need to be satisfied in each of these different channels to form gravitational wave sources. And then physical processes responsible for dynamical assembly. And I talked about some specific work that we did to form mass gap and intermediate mass black holes and what matters, what doesn't. And potential way forward, I think it's very interesting to find enormous compact optic binaries. And now we can find, I think, a lot of compact optic binaries with luminous companions. And in those, we can probably be able to connect the compact object to the metallicity and age of the progenitor. And that is going to help us enormously in updating our stellar evolution.
Thank you, Sourav. I'll take questions from those who will
Yes.
first.
But he will not wait for you.
Yes. And
Is there a evidence of elements within the star? It's not evident in the high mass scale problem, but can you say those structures are kind of examples for low mass stars where there are collisions?
See, chemically homogeneous evolution is not quite collisions. So, chemically homogeneous evolution happens when the stars actually did not collide, but because of the tidal sinking and the centrifugal force, you mix the whole stuff, and there is no core envelope separation. So blue stragglers are not chemically homogeneous.
now you can.
I have to, but the idea was one.
No, you
No,
don't.
it's a-
It's glad to see that these are from the first few catalogs, people are finding out the signature, that there are these bumps in the mass distribution of masses of the binaries, and some of for the heavier one. And they are saying that this suggests sort of hierarchical adjustment. But do you see any such signatures in your simulations to back up those theories? But the things which are like are very distinct, because you can really, I mean, it will be difficult to ignore that there are no bumps there, even though there are different parts.
So I think the bumps are real, and we haven't done enough simulations. So this is something that's right now underway. We do not know the results yet, but it will be. We are also very interested to see exactly what comes out in these situations. So the real issue there is ultimately what you see is what is observed, and it's a somewhat non-standard transmission from like what exactly was the metallicity distribution. So the metallicity basically tells you exactly what is the distribution for black holes, and then these are the black holes you get to play with, and so on. And then the other problem comes from exactly what's the Barth spin distribution. So, but if you assume something reasonable, it is possible to find some realistic expected mass distribution. We do not have the results yet.
Of the piece. But even any metallicity or so on, meaning that the bumps you would be able to see, right? Because whatever class metallicity you start with.
Yes.
That will show that this is visible. My main problem is that suppose this is happening, like what you are seeing is integrated over the nature of the universe. So even if there are these hierarchical formations with different generations, it's getting smoothed out over different parts of the universe, right? So do you really see a bump or not is the question.
That's actually a very good point. I didn't think about it. So I always was thinking about the complicated, like integrated thing. But I agree with you. Just looking at a few simulated clusters, and if you can build up enough statistics, just to see just in some narrow parameter space of clusters whether we expect it. So it'll be a very good thing.
Okay, Bhushan.
So now you said because you take the starburst and simulate it, and so the question is we can try to do say it's not measurement or something by looking at only old starburst galaxies which are now quiet and our transformation sees 2 million years ago. Looking at those catalog, just saying all the binary metal mergers are coming from. Is there anything which we will gain by looking at this kind of scenario? Or do you give it to us?
So you were so let me try to rephrase this question, and you tell me whether that's correct. So you were saying that instead of a cosmologically integrated thing,
Yeah.
can I look at a particular galaxy and it has its particular family of stellar clusters and say, okay, I know the ages and properties of all these clusters. if I simulate only these, then what do I find? And whether I can somehow relate the host to observed merger correlation. It is
Not using full catalog, right? If people use NTSS or other, can we use just these catalogs with some particular skill motivation?
You want a prayer to be given to Galaxy.
Yeah. So which may work.
So it's possible. So I will tell you one challenge. So what the clusters that you observe are what's surviving. So each galaxy will have a lot of dissolved clusters. And many of these dissolved clusters are accreted onto the center clusters that you cannot see anymore, can significantly contribute to the overall detectable population. But that also maybe can be modeled if we know the galactic potential. Okay. But my approach to this was if we can somehow create a cosmological globular cluster or dense star cluster of this kind. So clusters of this kind form with that metallicity at that redshift in that galaxy, and if we have all of, then it will become very easy to do a statistical study. So because it's not necessarily that that galaxy will really contribute something exactly in the narrow band in redshift that we observe today, but it may be very interesting.
I would like to add here that the galaxy also, single galaxy also have a globular clusters, which are come from different galaxies.
Exactly.
So you cannot just say that they're on the Hubble cluster, whether survive or not, they may have an external origin.
Exactly.
It is already observed.
This is how it goes. Even in the Milky Way, guys finding all kinds of strings.
My mention of side, they just instead of adding weights to galaxy catalog, because we might not have classically on that process. Can we use something else as a better proxy crossing to the weights, which has some historical information about Tata?
So my style of doing that, something similar would be like coming from from help from cosmological situations.
In your mass range, it will not help. You want back to the 5, that will be through
Prescriptions.
No, but basically what is, see, if you say that they are proportional to n stars, or proportional to total number of stars formed, either use stellar mass as an indicator or blue color as an indicator. But that won't work here because it will work in a scenario where you don't worry about forming these binaries through clusters, right? You don't use dynamics of clusters to form binaries. But then the question is that for a given mass, suppose if I take 10 to the 10 solar mass, can I have different whatever mass functions for mass function, metallicity distribution, this is what RH distribution, which can come from various, could be coming from some other galaxy or episodic activity of star formation in the same galaxy, whatever. It's a lot more convolution. Anyway, I was suggesting to him, like in simulation, for example, forget about this mass array. One could just look at the clumping distribution. Nothing to do. See, don't ask a very fundamental question in the first day itself. If you can understand that clump distribution or clump mass function, whatever physical quantities it will depend on, that could be an indicator to start with to have. I thought like we can have 2 times 10 to the 4 10 to the 5 we may resolve some of this simulation. As so if you say that 10 to the 6 is what I want, I have at least 20, 30 particles, all clusters in my simulation. That can be that we can try and see like whether because then all the physics will be there. You can look at all of them whether they have homogeneous metallicity, are they coming from the same parent halos or are they migrating? See, simulation you can do whatever. But you have to define what is a globular cluster. Yeah.
So very interesting and interesting work. I just had a question on this basic of the dynamics. In globular cluster, the star cluster is basically collision mode. So I'm just thinking what, and then very sensitive to Japan, the orbital structure will depend how you sample the orbits. So the scattering. So what kind of integration routine that are preferred? Because that symplectic nature is there.
Here. So we
In sense of symplectic nature, how do you go up to 10 layers? And how do you save the scattering due to the
So this is a very good question. So so there are two ways of application. So first of all, I did not talk the different computational methods. So there is the direct involvement. So where you have n number of massive objects and you are actually calculating the gravitational pairwise gravitational forces. Yes, so grapes or nowadays. So that's there are modes to do that, but it's not realistic to expect them to model anything above few times 10 to the 5, n or few times 10 to the 5. It's follows. Okay. Then there are these two different ways to do approximation, assuming that when n is sufficiently large, orbits change on a significantly longer than dynamical scale. Okay. So one is called the orbit following averaging. So this is developed in Princeton. And the main use case is if you are trying to look at exactly how orbits fall around the center of the galaxy. So there you slowly evolve the underlying potential using a Fokker solver, and then you basically follow orbit of representative particles around and in a not sure whether symplectic way or not, but it can track resonances. What we do for dense star clusters is called the orbit averaged. So this was first shown by Henon in 1971 that it works. So basically, the idea is in each step, all particles are interacting with all other particles. And in the gravity field is particularly interesting because the distance doesn't matter. So your volume grows as r square, and your force decreases by r square, so they cancel each other. So you need to take into account all the interactions. But because of this, also, most of the interactions are weak in nature. So that means that each star is just doing a very little bit of thing. So you can show that when n is very large, then to get significant change in the orbit, you need to wait for a relaxation time, which is dependent on n over log n time. So the Henon's approach was, so in each time step, the orbits are changing, like kind of like doing a random, as an effect of the cumulative forces. But all these tiny random ones can be represented as a super encounter on a relaxation time, which is the net effect throughout many integrated over so that's the assumption we do. And then the only thing that we need to do is we need to tune exactly what is the angle distribution for these super encounters. That comes from the calculation of the Fokker-Planck collision term. Okay. And so it has been shown by your group that the results from this simulation match very well directed body force, as long as n is above a few times 10.
I was wondering, how do you basically you are thinking ourselves what response does how do you what are you concerned?
Angular momentum and energy.
That's okay.
And if you keep track of all the loss physics, so for example, stone encounters is not 2%, so you need to take into account like mass loss from stellar evolution, into account and so on. And the energy conservation is very.
Think, pardon me.
Okay, last question.
So you take that consider composition system. So that so how you take the track of the phase space, like when they were when in this simulation, when they are like complex object, the class two recombinant object. So how they are like maintaining the
That's a very good question. So we go back and forth between n-body and focal. So initially we start with an n-body test. So individual stars, individual planets. And then we check whether, okay, should I do stellar evolution on this? Should I do binary interaction on this? Should I do strong encounter on this? If not, let's do relaxation on this. Okay. So after relaxation, so how do we do relaxation? We say orbital. Okay. So now we go from n-body to focal. Okay. So each star is now a split. And that creates a potential. Then we do the focal plumb. And then now we find the new orbits to the changing energy and angular momentum based on all these weak encounters. So using these new orbits, we then do a Monte Carlo. We just sample, okay, so this star has this orbit. What is my likelihood of finding the star? Okay. So based on this probability, we find these stars in different locations with different velocities. And then we went back from focal plumb to n-body again. So again, we have stars and then they have their positions and velocities and so on. And then we again ask, should I do stellar evolution? Should I do binary interaction? Should I do strong encounter? Should I lose the star because tides? So all of that. And we keep repeating this. So whenever we are trying to track something that is not happening on a relaxation time scale, we go back to the n-body. That's the Monte Carlo. So once you find the new orbit, you Monte Carlo and find that. Yes, it is public. It's on GitHub.
Okay, so let's thank once again.
What's
Yeah, for some time.
No, one of the things that we are thinking is like typically the number of globular clusters is also a function of the mass of the head.
Yes.
So if these things are happening, I mean, if the most dominant channel is this dynamical channel, then you expect in the clustering signal that they should have a particular bias
Yes.
with respect to large scale structure.
Yes.
And so now slowly, hopefully, we'll start to detect clustering of these gravitational remnants. Then once we get estimates of the bias, then you can start to again distinguish.
So the idea was like from cosmological simulation for zoom simulation,
Yeah.
or whatever, it can guide us like exactly. So instead of having like a homogeneous, constant formation distribution.
Yeah, so this clustering will help, I think. I want to write that paper to quite some